Hello. So we will now do the Chapter 7 review worksheet. I encourage you to do this along with me, to pause the video and to see if you can get these answers right. But this is a nice little review of the stuff in Chapter 7. Of course, I'm going to go through this relatively quickly. So I thoroughly explained the concepts that are in here in previous videos in the Section 1, Section 2, and Section 3 video notes. So I certainly encourage you to look at those if you're confused about any of this stuff, or obviously send me any questions that you have. But so let's look at this review worksheet. So in context one, it says the owner of a warehouse wishes to estimate the proportion of boxes in the warehouse that have water damage. Unbeknownst to him, 12.7% of all the boxes in the warehouse have water damage. He takes a random sample of 600 of the boxes and finds that 84 of them, which would be 14%, 84 out of 600, have water damage. So in any context we always say, what is the population of interest? And so the population of interest, that's the whole group we want to know something about. And that is going to be all the boxes in the warehouse, all the boxes in the warehouse. That is the whole group of people, animals, or things, in this case, things that we want to know something about. Number two, what is the sample? Well, the sample is going to be the part that we actually study, actually look at. The sample is the 600 selected boxes, the 600 selected boxes. So that is our sample. All right, number three, what's the parameter? The parameter is what we want to know. It's a number that describes the whole population. And so in that case, it would be this 12.7%. 12.7%. It is a proportion. P is equal to 0.127, all right, which is the proportion of all of the boxes that have water damage. So if you wanted to describe that in context, that would be the proportion of all the boxes, the proportion of the population that have water damage. That is what we want to know. And thus, that is the answer to number three. So number four, what is the statistic? The statistic is in essence the value that describes the sample. Well, what, in other words, the 600 boxes, and our SIC, find that 14% of them, that is our p hat. We're interested in a proportion here. So our p hat, which is 14%, 0.14, and that would be the proportion of the 600 selected boxes, the sample, the 600 selected boxes that have water damage. And that, of course, is an estimate of our parameter. Okay, on to number five. Describe the sampling distribution of the sample proportion here. The sampling distribution is every value p hat could possibly take in repeated sampling. Okay, that it is every value p hat could possibly take. And when you're asked to describe the sampling distribution, so what it would effectively be, of course, we have to describe its center, its unusual values, its shape, and its spread, is our sampling distribution is going to be centered around the parameter, which is p is equal to 0.127. And it is every possible value that p hat could possibly take. If we took many, many samples of size 600 and each time find the proportion of water damage and all the possible values of p hat, that is what the sampling distribution is. The center, so we have to the center is going to be the p of 0.127. So the mean, the average of the p hats is going to equal p, which that's 0.127. All right, now we'll talk about the unusual values in a second, but what about the spread? What value describes their spread? And that is our sigma. What is the standard deviation of the p hats? And on our little formula sheet, it says this. It would be the square root of p times 1 minus p over n. So that would be 0.127 times 0.873, just that times 1 minus that, and then over our sample size, which is 600. And so that, in fact, is approximately equal to 0.013596. Getting plenty of significant digits there. So that would be the spread. And then the shape. The shape is going to be approximately normal. And why is that? And our little rule for proportions is n times p and n times 1 minus p are greater than or equal to 10. And that, by the way, and so that would describe, so describing the distribution, you'd say the center is that, the spread is described by the standard deviation of that, the shape's approximate normal, and by saying it's approximate normal, that takes care of the unusual values or the outliers. Then on number 6, it says, why is it approximately normal? And the reason it's approximately normal is n times p and n times 1 minus p are greater than or equal to 10. So when you say 600 times 0.127, all right, that is 76.2. And then 600 times 1 minus that, which would be 0.873, and that is 523.8. They're both greater than or equal to 10. And that is the central limit theorem. The central limit theorem for proportions is that if both these are bigger than 10, the shape will be approximately normal, but both of them have to be bigger than 10. So thus, that's the answer to number 6. On to number 7. What fact allows you to use the formula for the standard deviation of the sample and distribution? Well, our population size, our sample size can't be more than 10% of our population size. Okay, so in this case, you would say there, since our sample size is 600, you would say there must be at least 6,000 boxes in the warehouse for our sample size to be less than or equal to 10% of our population size. The population has to be at least 10 times the sample size. So there you go. So that's the assumption we have to make. All right, so that's number 7. Let's look at number 8. So number 8 says, assuming that 12.7% of all the boxes in the warehouse have water damage, what is the probability you get a sample value as large as 14% or larger? So when you think about our sampling distribution, here it is approximate normal. What's the probability you're going to get 14% or more? In other words, does this 14% in the sample, does it give you reason to doubt that? Okay, so the way we would do that is we would say normal CDF. And it said 14% or more, so it'd be 0.14 to infinity. Our mean is 0.127, and our standard deviation is the square root of 0.127 times 0.873 over 600. Of course, we label this as lower bound, upper bound are the mean of our p-hats, the sigma of our p-hats. And let's see what we get. So let me grab my little calculator here, and let's do this thing right there. So we would say second vars right there for distribution. And then we would go normal CDF. We go 0.14 to infinity, just a huge number like that. And then our mean is 0.127, and our standard deviation is the square root of 0.127 times 0.873 divided by 600. I believe that's right. Yes. So there we go. And so then we paste and hit enter. And so it is 0.16945. 0.16945. That is distinctly bigger than 0.05. So if this was below 0.05, we would have reason to doubt the 14% figure. Since it's greater than 0.05, this is nothing unusual. In other words, it wouldn't be surprising, or I'm sorry, if it was below 0.05, it would give us reason to doubt that that is the true mean. Okay, but so it's above 0.05, so we have no reason to doubt the claim in the problem. So in regards to number 9, it says, does the result give you reason to doubt that figure? And we would say, no, we have no reason to doubt it because 0.16945 is greater than our alpha of 0.05. That's sort of our rule of thumb there. So 14%, 0.14, would reasonably reasonably occur by sampling variability, just by random chance, sampling variability. So there you go. There's kind of different ways you could word that, but that's certainly one of the ways. So that's how you do number 9. Okay, so let's go to number 10. All right, so number 10 says the owner decides to take another sample of size 3000. In this sample, he also finds that 14% of the boxes have water damage. What is the probability of getting a sample proportion as large as 0.14 or larger, assuming that the 12.7% figure is correct? So everything's the same in this problem as in this problem. The only thing that's changed is the sample size. They increased the sample size from 600 to 3,000. Everything else is the same. They get 14%. The population is 12.7%. So let's find this probability. So this probability said the sample size is 3,000, but it's the same thing, the same calculation as in number 8 in essence. So we would say normal CDF. And we would go 0.14 to infinity. And so this is 0.127, and this is the square root of 0.127 times 0.873 over 3,000, like that. That is our lower bound. That is our upper bound. That is the mean of our p-hats. That's the sigma of our p-hats. Please write that every time, because otherwise you'll just get partially correct. And so let's see what we get. It is 3,000, right? Yeah, it is. All right, and so I'm just going to go up there and grab that command like that, and then change this to 3,003, 1, 2, 3. And so boom, and boom. And so 0.01624, 0.01624. That is distinctly below 0.05. And so that would give us reason to doubt that the 12.7% figure is right. In other words, if it's claimed that only 12.7% of these boxes have water damage, and we take a random sample of size 3,000 and get 14%, we would say, wait a second, we got significantly more in our sample. We think that more than 12.7% of the boxes in here have water damage. That's what our sample is telling us, assuming we didn't get a biased sample. But randomness should take care of that. So number 11 says, does this result give you reason to doubt? Yes, it does. So number 11, yes, we have reason to doubt, because our p-value, which is what we're going to call this later in the year, 0.01624 is less than 0.05. So 0.14 is unlikely to occur just by sampling variability. And once again, the only difference in this problem than what above it is the sample size. And so that's the answer there. Number 12, it says, why are the conclusions drawn in number 9 and number 11 different, even though they both had the same sample proportions? And the reason is the bigger sample size creates less variability in your sampling distribution. Okay, and so this is the way I would word this, and I explained this in the other videos. But the larger sample size creates less variability in the sampling distribution. So a value a certain distance away from the mean, here 0.013, and that's how far it is from 12.7% to 14%. That is how far it is, or higher, are less likely. The bigger sample size creates less variability. It makes you more certain about things. So values away from the mean are less likely to occur, and with a bigger sample size. So that is that. Okay, so let's go on. So that's number 12. So let's go on to number 13. So, and that would be context 2. So number 13 says this: the warehouse owner in context 1 also wants to estimate the mean weight of the boxes in the warehouse. So we have a mean now. So the one up above is proportions, and this one's means. All right, unbeknownst to him, the mean weight of all the boxes is 30.6 pounds, and the standard deviation is 5.7 pounds. He takes a random sample of 30 of the boxes and gets a sample mean of 29.9 and a sample standard deviation of 5.9. So what are the parameters? You got the same population, by the way, all the boxes in the warehouse. The sample is now the selected 30. What are the parameters? What are the numbers that describe the entire population? And that would be unbeknownst to the mean weight of all the boxes. So in regards to number 13, we would say, well, first of all, we have the mean of all the boxes. The mean weight is 30.6 pounds. And then the other number that describes the whole population would be the standard deviation, which is sigma, which would be 5.7 pounds. So those are our two parameters right there. So number 14, what are the statistics? Statistics are numbers that describe samples. And so in this case, sample size 30, their mean weight is 29.9. So it's a mean X bar. So that would be 29.9 pounds. Once again, mean, mu and X bar are both means. Mu is of the whole population, X bar is just of your sample. And then the standard deviation of the sample is S, 5.9 pounds. Okay, so that is our other statistics. Of course, X bar is an estimate of mu, S is an estimate of sigma. So that's 13 and 14. So let's look at 15. So 15, it says, what is the sample distribution? Very different from the sampling distribution. The sample distribution is every number in the sample. We have 30 values in the sample, 30 things in the sample. And so it is the 30 numbers in the sample. So it would be, and these are weights of boxes, and you would say the weights of the 30 boxes in the sample. That would be the sample distribution. All right. And then I didn't include a question about what the sampling distribution is, by the way. The sampling distribution is every value X bar could take in repeated sampling. So it didn't ask that here, but certainly, you know, I talked about that thoroughly in section 7.3. But anyway, number 16, assuming the mean weight of all the boxes is 30.6, and the standard deviation is 5.7, which is claimed up in the problem. All right, what is the probability of getting a sample mean as low as 29.9 or lower in a sample of size 30 just by sampling variability? Well, so our sampling distribution here, okay, is going to be centered at 30.6 with a standard deviation of 5.7. And so find the probability of 29.9 or lower. So we would say normal CDF. So from negative infinity to 29.9, those are all the values that are lower than 29.9. That is my lower bound. That is my upper bound. All right, the mean of my sampling distribution to population mean 30.6. So 30.6, that is the mean of my X bars. What about the standard deviation? So let me remind you, when you're dealing with a sample and a sampling distribution, all right, so for a mean, that is the mean of your X bars, sigma over the square root of n. You have to divide by the square root of the sample size. So this would be 5.7 divided by the square root of 30. So this would be 5.7 divided by the square root of 30. That is the standard deviation of my X bars. So let's see what that is. So we shall do that. So we shall say second vars, which is distribution, normal CDF. And so we are going negative infinity. Hit the negative sign below the 3, not the minus sign. That's a common error. So negative infinity, just go negative and then 9 billion. So that would be like negative infinity effectively. And so then the upper value is 29.9. And then our mean is 30.6. And then our standard deviation is 5.7 divided by the square root of 30. So that'll work right there. Boom, boom. And so we get 0.25059. So that would be 0.25059. And so there you go. And so that's how you do that one. And so that is certainly above 0.05. So that gives us no reason to doubt the claim in the problem. Okay. In other words, this difference is very plausible that would happen due to sampling variability. So number 17, does this result give you a reason to doubt the 30.6 figure? No. So we would say no, because 0.25059 is greater than 0.05. So 29.9 is reasonably likely to occur by sampling variability. It doesn't give us reason to doubt the 30.6 figure. So there you go. Okay, and so number 18. Number 18, there we go. All right, the official in context 2 wants the standard deviation of the sampling distribution, the sample mean, to be at most 0.5. How large should the sample size be? All right, so the standard deviation of our sampling distribution, so on our little formula sheet, the sigma of the x bars is equal to sigma over the square root of n. So he wants this thing to be at most 0.5. So 0.5 be greater than or equal to, he wants this thing to be less than that. And so our sigma is 5.7 divided by the square root of our sample size. And so this is a common question, because anytime you're doing a study, you need to figure out how big your sample size is going to be. And so what's going to guide you is how big you want the standard deviation in your sampling distribution to be. So we'll just solve this for the square root of n. So I'll multiply both sides by the square root of n. So this would lead me to the square root of n times 0.5 is equal to 5.7, and that would cancel. So it's 5 divide and then divide. So I get the square root of n is equal to 5.7 divided by 0.5. And so she can be 5.7 times 2. So I'll say 5.7 divided by 0.5. And so it gives me 11.4. So the square root of n, and this is greater than or equal to, greater than or equal to 11.4. So I just square both sides. So I get squared, and so I get 129.96. So n is greater than or equal to 129.96. You always round up, because your sample size has to be an integer. Okay, and even if this had been below 0.5, like if it has been 129.16, you would still round up. And that guarantees that our actual standard deviation will be a little bit less than 0.5. So you always round up. Okay, so that's how you do that. All right, another context, number 19. All right, context 3. 48% of pine trees in a forest have a particular fungus. 41% of maple trees in a forest have a fungus. An SRS of 140 of the pine trees in the forest is taken, and an independent SRS of 180 of the maple trees in the forest are taken. In each sample, the proportion of trees that had the fungus is noticed. What is the mean of the sampling distribution of the difference in the sample proportions of pine trees and the maple trees that had the fungus? Pine minus maple. So what we're doing is we're subtracting, all right, the mean for the pine trees, and we're subtracting the sample mean for the maple trees. Okay, so what is this going to average in a large number of samples? And so in essence, the mean, so that is our difference. So what is the mean of our differences? Okay, in other words, the mean of x bar sub p minus x bar sub m, and that is on your formula sheet. So, and I'm sorry, this is with a proportion, my bad, forget that. This is with a proportion. We're dealing with proportions here. Talks about in essence, a proportion. So it is the p hat. It is the p hat in the pine trees minus the p hat in the maple trees. That is our difference. And so the mean of our p hats, for a 2 proportion, you just subtract the population proportions. Okay. And so that is going to be equal to 48% minus 41%. So that would be 0.48 minus 0.41, and that is equal to 0.07, like that. Okay, and so that's the answer to number 19. Number 20, what is the standard deviation of the sampling distribution of the difference? So the standard deviation, number 20, the standard deviation of our difference, p hat sub p minus p hat sub m. All right, and so that is that guy right there. It's a little bit little bit messy, but it's not too bad. And so when you plug in to that formula, you would get this. And so that would be the square root of the first proportion, 0.48, times 1 minus that, which is 0.52, over our sample size. Let's see what our sample size is. So our sample size for the pine trees is 140. So that'd be 140. All right, plus, and then do it for the 0.41. So that's going to be 0.41 times 0.59 divided by our sample size there, which our sample size there is 180. So 180, okay? And so then when you find that, that ends up being, when you use your calculator to find that, that ends up being 0.0559173, putting plenty of significant digits there. And so that's how you do that. Number 21, what is the probability the sample proportion for the pine trees would be at least 0.05 more than the sample proportion for the maple trees? Now up here, we have subtracted pine minus maple, okay? And so for number 21, so the probability that pine minus maple is at least 0.05. And so we would say normal CDF from 0.05 to infinity. 0.05 to infinity, right? 0.05, at least 0.05 would be 0.05 to infinity. Our mean is 0.07 and our standard deviation is 0.0559173. And so this is our lower bound. That is our upper bound. That is the mean of our differences. That is the sigma of our differences, which are those things written up there. And so when you do that, let's see what happens when we do that. And so we shall say second of ours, which is distribution, normal CDF from 0.05 to infinity. Our mean is 0.07. And our standard deviation is 0.0559173. And so we go like that. And so that's 0.6397. So that would be 0.6397. All right, approximately. And so there we go. So it happens more than half the time. So that is the answer to number 21. All right, and let's move on to our last context. Context 4. So context 4 says this. So it says the mean height of the elm trees in a forest is 37.9 feet with a standard deviation of 5.4. So this is quantitative data that deals with the mean. We're not dealing with a proportion like we were in the previous context. The mean height of the dogwood trees in the forest is 13.8 with a standard deviation of 2.9. A random sample of 40 of the elm trees is taken, and an independent random sample of 55 of the dogwood trees is taken, and the sample height for each sample is found. What is the mean of the sampling distribution of the difference in sample means for elm trees minus oak trees? Okay, so we are going to subtract our two distributions. So the mean of our difference, okay, the mean of X bar sub elm minus X bar for the dogwood, you just subtract the two means. It's going to be 37.9 minus 13.8, and that would be 24.1, and it is feet. Make sure and put the units. So that is that. So to find the mean, you just subtract the two population means. All right, so then for number, so that was 22, and then so for 23, so 23 says, what is the standard deviation of the sampling distribution of the difference in the sample means? So the standard deviation, and once again, that's on your formula sheet. So if you go for means there, if you go for means, there's the mean, there's your standard deviation. Right there, there's your formula, the square root of standard deviation squared over the sample size plus the same thing for the other population. So the standard deviation of the difference, X bar sub E minus X bar sub D, is equal to the square root of, okay, and then our first standard deviation for the elm trees is 5.4, so it's going to be 5.4 squared over our sample size, with the sample size for the elms is 40, so it's over 40, plus the standard deviation for the dogwood trees is 2.9, the sample size of 55. So this would be 2.9 squared over 55, like that. And so when we use our calculator to find that, according to my records, you would get about 0.939100015. And so that's how you do that problem. Number 24. So number 24 says, what's the probability that the difference in the sample means will be less than 22? So we would say normal CDF. Less than 22 would be negative infinity to 22. That's all the numbers that are less than 22. That's my lower bound. That's my upper bound. My mean is 24.1. That is the mean of my differences, okay, which is that. And then the standard deviation, the sigma of my differences is 0.939100015. And so let's use our handy calculator to figure that out, as we've done many times. And so second distribution, normal CDF, negative infinity, negative 9999999 to 22. Our mean is 24.1, and our standard deviation is 0.939100015. And so that's 0.01267, about 0.01267. In other words, it's really unlikely to occur. If this really is the difference, it would be unlikely to get that difference in a sample. So, and so that is the answer to number 24. And then 25, some guy wishes to decrease the variability in the sampling distribution. What should he do? To decrease variability, the main thing you have to do, increase the sample sizes. And there are two samples here. So increase the sample sizes. That decreases your variability. That would make your standard deviation smaller, and it makes you more precise about things. And that's it. That is a very, I realize I went really quickly through that, but if you have any questions about that, please let me know. And I wish you much luck in regards to working with sampling distributions. And I just hope you have a great day.